So here we are in section 3.4. We have more proofs to do. These are official proofs, like the proofs of the last section. And what I mean by official proofs is that these are proofs that appear on the theorems handout that I gave to you. And these are proofs that we will make use of later on in the class. And remember that basic point about a theorem once it has been proven. Once it has been proven, it can then be used as a reason that justifies a line in a later proof. We don't have to recreate the details of that proof. We can just simply make use of the proof by its name. All right, so the proofs in this section have to do with parts and wholes, and they all apply ultimately to both segments and their parts and angles as well and their parts, but we will only do the proofs for segments. The proofs for angles would be exactly similar, and remember what we said before, if we've given a proof, and the other proof that strictly would have to be given is exactly similar in structure to the one that has already been given, then we don't have to give that second proof. We can just simply point out that it could be done in the same way. Yes, we are rigorous in this class. Yes, we prove results in this class, but we do not torture ourselves with unnecessary work. All right, so first of all, the midpoint and angle bisector theorems. These are existence theorems, ultimately. The midpoint theorem says that for every segment, a point exists that is its midpoint. The angle bisector theorem says that for every angle, a ray exists through its interior from its vertex, of course, that um, is its bisector. So these two theorems assert existence, and these will be extremely important for us later on when we take on a topic that is called construction. I'll just hint at what that is. In construction, we actually add to a diagram as given to us. Perhaps we place a midpoint in the diagram, perhaps we place an angle bisector in the diagram, but to do that, we'll have to have a guarantee of the existence of the object that is drawn into the diagram. And the midpoint and angle bisector theorems will do that for us. Now, as for the proofs of these, well, they're really obvious consequences of the ruler and protractor postulates, so we won't actually take the time to prove them. So, for instance, the midpoint theorem, um, just every segment has a length, the ruler postulate says, and that's obviously true, which means, of course, that we can take that length and divide it in two. And when we do that, we will have, as a matter of fact, the midpoint. All right, so let's actually prove some theorems now. So let's prove the halfway theorem. So what it says is this. It says that if C is the midpoint of a segment AB, okay, so let us assume that we're given the midpoint, then AC equals BC equals half AB. Okay, so AC and BC are the two parts that are created by the midpoint, and each has half the length of the whole. And there's a version of this for angles as well, of course. It says that the angle bisector creates a pair of sub-angles, and the measure of each is half the measure of the whole. And as I said before, we'll do the segment version, and we'll do it column style, or if you like, table style. And the angle version would proceed in just the same way. So let's say that C is the midpoint of segment AB, and this is a very simple relationship, but I do think it would be helpful to have a picture for this. So let's draw one. So we have a segment AB, and we have a point C that is the midpoint. Um, and do note something here. I've pleaded with you to take care about what definitions state and what they do not state. The definition of midpoint does not state that each of the subsegments created by the midpoint is half the length of the whole. That is true, but it's not part of the definition. All the definition says that that midpoint creates a pair of subsegments that are equal to one another. It never introduces the concept of one half. That one half is true, but it has to be proven, and that's what we're about to do. So the given is that C is the midpoint of segment AB, from which it follows, of course, that AB is equal to BC. And as I just pointed out, that is the definition of midpoint. And of course, MDPT is short for midpoint. Now, how do we actually get to the one half? Well, there's another idea at work here, and that's found in line number 4, where we say that AC plus BC is equal to AB. Oh, that means that the whole is equal to the sum of its two parts. Well, how do we know that to be true? Well, we know that C lies on AB. That's really part of the given. And then we have applied the segment addition postulate, which says that the sum of the two parts is the whole. And then look at line number 5. AC plus AC is equal to AB. That's just like line number 4, except the second BC, or the second part of the left-hand side, the BC, has become AC. So what allows for that important word here? substitution? Well, what allows for that substitution is that on line number 2, we were told that AC is equal to BC. So when we combine 2 and, I'm so very sorry, but notice that I skipped from 2 to 4. So sorry, it doesn't really make any difference in the end. So we make use of lines 2 and 4. And then what we applied was substitution, as I said just a moment ago. And if you were to, maybe this is actually a point, a place where I can make an important point. If you, for instance, were to skip a number, and the way that I've done is you number the lines of a proof, of course that's not a mistake in the proof. It has nothing to do with the logic of the proof ultimately. Of course, one would like to avoid that. You don't want to confuse the reader, but ultimately it's not a defect. It's not a logical defect. So I would never count off if you were to do something like that. So let's pretend that I actually did this on purpose. And that I wanted to make the point that I just made. All right, so let's look now at line number 6. What happened is that AC plus AC became double AC, then the right-hand side remained the same. So what we did is just a bit of substitution to simplify an expression down. That is, AC plus AC was replaced by double AC. And then we took that line number 6 and divided both sides by 2. So that's line number 6. And to that we applied the division postulate. And then we simplified down. I mean, typically after we divide, we have to simplify the results down, which for us is substitution. Simplification always is substitution. So there it is, SU, dang it. I have to figure out a way to make that not happen. It's probably required that I would buy new hardware, perhaps a tablet on which to write. I guess I'll leave it this time. And then let's see. Oh, okay, so we have AC is AB over 2, which is part of what we wanted to prove. But then we also say on line number 9 that BC is AB over 2. Now we could go through this whole process again of segment addition and substitution and so on. But do notice that on line number 2 that we know that AC is equal to BC. So whatever is true of AC is also true of BC. So if AC is AB over 2, then BC is AB over 2. So what we did is we took lines 2 and 8 and we applied to that substitution, which in this case could also be called transitivity. All right, so there's a completed proof. All right, so let's discuss some of the other proofs I'll have you do. And only one of them we will actually do ourselves. The others we'll just talk about a little bit. So here's the statement that you will prove. If two segments or two angles are equal and each is divided in half, then the halves created are equal. Or as Euclid would have put it, halves of equals are themselves equal. You'll do this in the problem set. But here's the diagram with which you will work. So notice what we are given, two equal segments, namely AB and DE. And we're given that C is the midpoint of AB and that F is the midpoint of DE. And what follows is that AC is equal to DF. Also, of course, that BC is equal to FE and that BC is equal to DF and so on. That is, all the parts are equal. But we'll prove one instance of this, namely AC is equal to DF. And then, of course, in the same way, one could prove that all the other pieces are equal as well. So you will do this. The many parts theorem, often quite convenient to have, so we don't have to reprove it in later proofs. It says that if a segment or an angle is divided into two or more parts, multiple parts, let's say, then the whole is the sum of the parts. Well, of course, we know if we have two parts, then by the segment addition postulate or the angle addition postulate, the sum of those two parts is equal to the whole. But strictly the segment addition postulate and the angle addition postulate don't tell us what to do if we have more than two parts. So that's what's covered in this particular theorem. If we have many parts, 2 or 3 or 4 or 12 or 12,000, whatever, the sum of all of them together is equal to the whole. And so then here is the setup. We'll do 3 parts. And of course, if you could do 3, if you get the idea behind that, you can do as many as you like. So this is a kind of representative proof. So we have a segment AB with 2 points in its interior, C and D, that creates 3 component parts, AC and CD and DB. And we will say that the sum of those 3 is the whole. As for how you actually do this, well, I'll give you a hint. You're going to use segment addition postulate twice. Okay. And remember, segment addition says that the sum of 2 parts is the whole. So you might say, for instance, that AB is AD plus DB. That is, AB is AD plus DB. Certainly segment addition can do that. And then you can use segment addition to say that AD is AC plus CD. Yeah, so it's basically segment addition twice, and then you'll have to think about how it is that you combine those together to get your conclusion. And then we will have the conclusion, and we'll freely apply this conclusion that if you've got any number of parts at all, if you add them all together, however many, that will equal the whole for both segments and angles. Now, equal parts equal wholes. It says that, okay, so let's say that we've got like a segment and it's divided into some number of parts, and another segment, and it's divided into some number of parts. If we can pair off those parts in such a way that the paired parts are equal, then the wholes are equal too. That is, equal parts results in equal wholes. So here's a diagram to illustrate. And of course, the same will be true for angles as well. Let's say that we know that AE is equal to CF. That is, a piece of one segment is equal to a piece of the other segment. And then moreover, EB is equal to FD. So a second piece of one is equal to a second piece of the other. Then it follows that the wholes, that is AB and CD, are equal. And guess what? It's going to be segment addition postulate and probably substitution, because those equations in the given allow for substitution. I'll let you recreate, or not recreate, but create that proof in the problem assignment. Whole minus part. We're almost done here. And again, this is another one that I'll let you do. The final one we'll do together will be the final proof here that I discuss. It says that if we have two wholes that are equal, and we can pair off the parts of the two in such a way that all pairs except one are equal, then the final pair is equal to. Okay, so this, of course, feels like subtraction, doesn't it? So let's see, what are we given? We're given that AB is equal to CD, so the wholes are equal. And then we're given that AE is equal to CF. That is, we can pair off one pair of parts that are equal, and then it will follow that the other pair of parts, that is BE and FD, must be equal as well. So that feels very much like equals take away equals are equals. So this feels to me like it'll be the segment addition postulate and also subtraction. Okay, so I'll let you think about how those rules would be put together with others as well to give the proofs, but that's what it'll be. Okay. And then finally, this will be a really important one for us. It says that whole is greater than part. So if a segment or an angle is divided into parts, then the measure of the whole is greater than the measure of any part. Okay, quite plausible, quite intuitive. If I were to offer this up as a postulate, I'm sure you would accept it. But we don't need to call it a postulate. We can prove it, and so we will do that. But to prove it, I need to give you a definition of greater than. I know that you understand quite well what greater than is, but let me offer you a definition of which we can make use in our proofs. And this will be the definition that carries through the entire class. And then later in the class, we do have an entire chapter devoted to inequality type theorems, and they come up in some other places as well outside of that chapter. And in all of those places, we will make use of the definition that I am about to offer. All right, we say that P is greater than Q when there exists a positive quantity T such that P is equal to Q plus T. So let's pause and think about that for just a moment. So look at that equation. P is equal to Q plus T, where T is some positive quantity. Oh, so what really means, what's really happened is this, is that we took the quantity Q and we increased it. That is, after the sum was done, we had a quantity that was larger. So that should make perfect sense. And then, of course, that also suggests a definition of less than. If P is less than Q, then there exists a positive quantity T such that P is equal to Q minus T. So, so we took Q and subtracted a positive quantity, which means we decreased. And since we decreased, we are then less than. So here's an example. We know that 12 is greater than 7 because, well, fairly obvious, I suppose, but for our definition, this is true because 12 equals 7 plus 5. So that's the T right there, the positive quantity that got added in. So since we must add a positive to 7 to reach 12, this means that 12 is greater than 7. Okay. And of course, we could also say as well that 7 is 12 minus 5, which means that 7 is less than 12 because we had to subtract from 12 to get 7. Okay. Just a point of emphasis, and this is going to be really important in the proof that we'll see in just a moment. The point of emphasis here is that this quantity that we add to make greater or subtract to make less, that must be a positive quantity. So to apply this definition, we must know that we have a positive quantity. Okay, so here it is, the segment proof. the angle proof could be done in the same way, where we prove that the whole is greater than the part. So we will prove that AB, the whole, is greater than AC, the part, and also greater than BC, the part. Okay, and I tell you what, we'll do both. Though, of course, if you could prove that it's greater than one part, you could also prove that it's greater than the other. Okay, so what do we got? Of course, you know how to construct a table, right? So we have statements that come from some previous statement by some rule, that is some definition, postulate, or previously proven theorem. And let's see. So what have we got in the given? So we've got a segment with a point in its interior. So what we can do then is we can apply the segment addition postulate. Oh, let me say that, of course, we have the given, which I won't create because I'm lazy, but it's clear. In mathematics, laziness is acceptable so long as what you've done is clear. So let's see, we can apply the segment addition postulate, right? So we can say that AC, or no, I tell you what, I'm going to write it the other way around. Of course, the segment addition postulate doesn't care about the order in our equation, but there's an order that I prefer here. So I'll say that AB is AC plus BC. So that follows from our given by the segment addition postulate. And then, well, let's think about this for just a moment. Okay, so AB is, oops, I said this wrong. AB is AC. So let me go back and change that. So that's supposed to be AC. Oops, sorry. So I'll make that AC plus BC. Okay, now it's correct. So there are two ways to think about what this is. What this says. This says that AB is AC plus some positive quantity that's called BC. Also, it can be read as AB is BC plus some positive quantity, AC. And remember what happens when you add a positive? You increase, which means that the result is greater, which will mean that AB is greater. That's the result. But of course, we just assumed something here. We've assumed that both AC and BC are positive, and that's something that must be said because we cannot apply the definition of greater than unless we know that what has been added is positive. So how do we know that these are positive? And I'm going to go ahead and write that. So AC, BC are positive. Well, I invite you, and you can pause the video if you like to do this, I invite you to go back and take a look at the ruler postulate, okay? Now, part of what the ruler postulate says is that every segment, like AC and BC, have some measure, and that measure is positive, okay? So that's built into the ruler postulate for us. Okay, so how do we know that this then is true? Well, what we did is we worked on 1 because 1 tells us that we do actually have these segments AC and BC. And then since they are actually segments, the ruler postulate, this was the first clause actually. It's not really necessary to say this, but I'll say it so you can make sure to look for it. What it says in the first clause is that those are positive. Okay, so think about what we've got then. We've got that AB is AC plus a positive, which means that AB is greater than AC. And likewise, we have AB is BC plus a positive. So that means that AB is greater than BC. So this follows from both 2 and 3. Okay, the definition of greater than beats both the equation on line number 2, and it needs that we have positive quantities. So from lines 2 and 3, together with the definition of, how about just GT for greater than, we know this must be true. Right, so you've got a problem set. I've done a couple of the proofs with you, the other proofs that you will do, and I think you're in a good position at this point to get them done.